In Part 1, we explored the possibility of life in the inner solar system. Out of all of the terrestrial planets other than Earth, it seems like Mars is the most likely place to harbor life. Going beyond Mars, we start to leave the Goldilocks zone, or the theoretical zone in our solar system where life could survive on the surface. We are now heading towards the gas and ice giants, each with many unique and interesting moons. But can life be found this far out? The first planet after Mars is Jupiter. Jupiter itself is not at all hospitable to life as we know it. It barely has any form of water, it doesn't have a solid surface, and the winds and convection forces on the planet would drag down any microorganisms that try to form in the tops of the cloud layer. The deeper you go into Jupiter, the more the pressure and heat increases. The chances are very slim that life could exist here in these extremes. However, Jupiter has some moons where the conditions are much better. The biggest of Jupiter's moons, called the Galilean moons, are big enough to have differentiated interiors. Small moons and asteroids tend to be just the same throughout, like a rock. However, bigger moons will often have layers and cores. The second of Jupiter's Galilean moons, Europa, is actually one of the most likely places to find life in the whole solar system, but not on its surface. The crust of Europa looks extremely unusual with these fault lines running all over. This is because the crust is actually made of water ice, and beneath this ice sheet is believed to be a liquid water ocean that spans the entire moon. Evidence of this can be seen through the rotation of the crust, which is thought to have moved by up to 80 degrees, very unlikely to have happened if the crust and core were solidly attached. Another piece of evidence is something that has only just been confirmed in the old Galileo spacecraft data. Galileo actually detected water plumes or geysers shooting water far into space when it passed by the moon very closely. In 2016, the Hubble team suspected they might have imaged water plumes shooting 200 kilometers into space, and this rediscovered Galileo data has confirmed it. NASA considers the prospect of life here so intriguing that there will be a dedicated Europa Clipper mission due to be launched in about 4 years' time. The Europa Clipper will orbit Europa, passing through the water plumes, sampling the water that is ejected. We are not expecting to find fish blasted into space by these geysers, but the water samples will tell us what the conditions are like under the crust, and if there really is a possibility of life down there. Future robotic missions that aim to reach and traverse this ocean are still in the planning stages. Interestingly, while Europa is the most likely place to harbor life around Jupiter, it is not the only moon that probably has an underground, liquid ocean layer. 3 of the 4 biggest moons of Jupiter, Europa, Callisto, and Ganymede, all could have life under their surfaces. Callisto may have a water or ice layer up to 300 kilometers thick. Ganymede has at least one water ocean layer, but could also have several, all separated by sheets of ice. Ganymede is probably the second most promising moon of Jupiter, as the bottommost water layer could be touching rock. Water-to-rock contact could be an important factor for life to exist, as the rock provides minerals. Ganymede is already the biggest moon in the solar system, but data also suggests that its underground ocean could also be the largest. Ganymede will also be getting its own mission, this time from ESA, or the European Space Agency, and it will arrive about the same time as the Europa Clipper. You may be asking, why do these liquid oceans form under the surface of these moons? Surely being so far from the Sun means these moons should be frozen solid. Well, along with tidal forces from Jupiter, a predominant thought at the moment is that the moons generate heat through something called Rossby waves, also known as planetary waves. Rossby waves exist on Earth in its atmosphere and oceans and are caused by the inertia generated by the rotation of the planet. They are slow-moving kinetic waves, but over a whole planet or moon, they can store a huge amount of energy. This means the subsurface oceans on the moons could have a lot more energy than first thought, and may have currents and streams in them just like in Earth's atmosphere and ocean. Why do scientists think life could exist in these oceans away from sunlight and the Goldilocks zone? Well, let's remind ourselves of the factors needed for life. Liquid water is present in these moons. Liquid water is essential because biochemical reactions can take place in water. Water is also an excellent solvent that easily dissolves and carries nutrients and other compounds in and out of cells. Life forms are made primarily of water. In fact, our human bodies are more than 60% water. Conditions in the moon's oceans would be cold, but not too cold, as water is able to be in a liquid state there. Being this deep under the surface means it is also a protected environment from cosmic and solar radiation. However, there needs to be also essential chemicals and an energy source, which we can't guarantee exists at the bottom of these oceans. Let's compare these moons to life on Earth. Previously, scientists believed that the sun was the source of all energy for life on Earth. But as we explored the bottom of our own oceans, we found ecosystems that were completely independent from the sun. The organisms there relied on chemicals and energy released by hydrothermal vents. Bacteria there use chemosynthesis, not photosynthesis, to create energy for themselves. These bacteria coat the vent, where amphipods and copepods graze on them directly. Above them in the food chain are snails, shrimps, crabs, fish, eels, and a host more. Here the temperature is hot and the pressure is enormous, but if something similar to hydrothermal vents exists at the bottom of these moons' oceans, and that life isn't unique to only Earth, this is as good a place as any to look for life. Beyond Jupiter, there are 3 more planets and their moons. Like Jupiter, the planets are very unlikely to contain life themselves. However, some of their moons also share the same characteristics with the moons of Jupiter. Particular moons of note are Rhea, the second largest moon of Saturn, Titania, the largest moon of Uranus, Oberon, the second largest moon of Uranus, and Triton, the largest moon of Neptune. The most exciting moon with these characteristics, though, is Enceladus, a moon of Saturn. It has extremely active geysers which spew 250 kilograms of minerals and water into space per second at over 2,000 kilometers per hour. It ejects so much material that it has formed a ring around Saturn called the E-ring. Cassini, a spacecraft that used to orbit Saturn, was able to pass through these water plumes and detected carbon, hydrogen, nitrogen, and oxygen, all key components of life. There is definitely heat being generated under the ice crust, as can be seen in this heat map. These are the tiger's stripes of Enceladus. The evidence of hydrothermal activity, water, and essential chemicals means that this tiny moon could be the most likely place in the whole solar system to find life. Sadly, though, we are far from proving any of this. Enceladus does not have its own approved mission, and it will be at least 4 years until we get orbiters launched that will go to Jupiter's moons. Actually exploring the oceans is still a long way off. I can understand the problem, though, of getting a robot that deep into a moon, but it's a little disheartening to think that we won't see it happen for at least, I would guess, 30 years. Beyond the planets and their moons, we have dwarf planets like Pluto, Eris, and Sedna. If they follow the patterns we see in the larger moons, they too could have liquid water oceans under their surface. But again, we are very far from being able to prove that too. There are just 2 more curious places to look for life in the solar system. The first is Titan, the largest moon of Saturn. It is extremely cold and so is dismissed by some as uninhabitable. However, it is unusual from any other moon in the solar system in that it has a thick atmosphere with methane in it. In fact, the temperature is just right that liquid methane can form on the surface. The moon actually has a methane cycle similar to Earth's water cycle. There is evidence of seas, lakes, and rivers of methane and ethane on the surface of Titan. Other factors essential to life also exist there, including chemicals and minerals on the surface. Plus, the moon orbits mostly within Saturn's magnetic field, which means it is protected from solar and cosmic radiation. Theoretically, life forms could exist that replace water with liquid hydrocarbons. Such hypothetical creatures were taken H2 instead of O2, react it with acetylene instead of glucose, and produce methane instead of carbon dioxide. NASA had proposed a mission to investigate the lakes of Titan in the form of a boat. But again, this was sadly turned down. Personally, I think the lakes of Titan would be the most interesting to investigate, and the mission even seems a lot easier than burrowing several kilometers to reach a subsurface ocean. Maybe a space agency in the future will revisit this idea. The last place to look in the solar system for life is on comets. A long-standing theory is that life has propagated through the galaxy on the backs of comets, although it is quite an outside possibility. The Philae lander that visited the comet 67P Churyumov-Gerasimenko in 2004 was originally proposed to have life-detecting instrumentation on board. Sadly, this idea was laughed out of court, but as it turns out, the comet is rich with organic material and there are clumps that resemble viral particles. These findings are difficult to explain with prebiotic chemistry. For now, though, the concept of life on comets is heavily disputed, and so it will remain a remote possibility.